Right, welcome everyone. Thanks for joining us today. For those of you who don't already know me, my name's Derek Stewart. I'm one of the business development engineers here at Solid State Supplies. I'm joined today by Mihailo Raljic and Jenny Plunkett from Edge Impulse, and they're here to give you an introduction to machine learning on an MCU, or TinyML as it's commonly known. As you see, Jenny's going to run through a demonstration using their online tool showing you how to develop a TinyML solution using a Silicon Labs Thunderboard, which is one of these, which some of you may already know. This has a Cortex M4 processor on it. It also has a radio in there to do Bluetooth, Zigbee, Thread, but we'll not be using that today. We'll be using the Cortex M4, and there's an accelerometer on there, but there's also a MEMS microphone and various other sensors. So this is a very good tool for doing some TinyML. I'm sure you already know Solid State Supplies is an electronic distributor, which includes a number of MCU suppliers. So one of them is Silicon Labs, another is Microchip, and both of these Edge Impulse already work with to provide an optimized TML solution in their tool. However, we also have MCUs from the likes of GigaDevices and Holtek. Both of these can use the Edge Impulse solution. It just takes a little bit more to integrate in, like mapping the internal peripherals and things. But this process is fully documented on Edge Impulse's website, so it is actually applicable to any MCU. Many of you as well, I'm sure, will be new to artificial intelligence and machine learning, and it's a wide and can be a very complex subject matter. Today, hopefully, we can demystify this a little, so you can better understand what's actually going on at a technical level. And we hope that we'll be able to show you how you can harness the technology to benefit your own designs. You probably know, and if you ask someone in the street for an example of artificial intelligence, they'll probably mention something like Alexa, Google, like Hey Siri, or maybe even Tesla's self-driving cars. These are very high-end forms of artificial intelligence and very processing intensive. For example, the hardware used by Tesla's platform 3 that's currently out now takes input from 8 cameras, radar sensor that can do about 600 feet, 12 sonar sensors, and all this needs processing in real time on their own hardware, which consists of, I have to write this down, 12 2.6 gigahertz Cortex A7s, 2 gigahertz neural network accelerators, and a 1 gigahertz Mali GPU. So a bit beyond what we'll talk about today. Even Amazon, Apple, and Google's voice command solutions need to understand thousands of words and also know how to understand sentence structure so that they can work out what questions or commands you're actually asking. And to process all of that is done on large, powerful servers in the cloud. These are way beyond what we'll talk about today, but some of these can actually benefit from TinyML as well. For example, the voice command solutions actually use TinyML in the local hardware, or on the edge, as you've probably heard it called, to make the solutions more practical and efficient. An initial activation word detection algorithm is actually run locally, which once detected then starts streaming the audio to the cloud where the full language is done. So actually the local hardware on your Amazon Echo Dot, whatever you've got, can only actually recognize 5 words, and that is a form of TinyML. So if you have a look, you'll see that if you've got one, it can recognize you saying the word Alexa, Amazon, computer, Edge, and for some reason the word Siri. I don't know why, but somebody's maybe a David fan. So voice commands to recognize a limited number of words is an ideal candidate for TinyML, as today's MCUs are easily capable of processing a serial audio stream from a microphone. As you'll see when Jenny does the demo later, an accelerometer is also an ideal tool suited to TinyML. this can be used for monitoring motion of a person, or maybe vibration of like a motor or a fan. You can add a gyro to that as well if you want to, if there's any rotational element you want to have a look at. So that's another thing it can be used for. MCUs can also be used for lower resolution, low frame rate video analysis. I mean, I know this is normally done on higher end ones, and you'll all have seen videos with like people in crowds and then boxes around them saying person, man, woman, or whatever. But actually, TinyML can also be used on an MCU if it's lower frame rate. I mean, at the moment, I'm having a play with an a thermal image sensor that's 60 by 80 pixels from Mitsubishi that we do. And I'm looking to differentiate the thermal signatures of a person, an animal, and a fire. So, and we also have low resolution time of flight sensors from a company called Dsps. And these could be used in, say, industrial applications where you want to do 3D object identification in some TinyML applications. So at a very basic level, the TinyML design process consists of a collection of lots of examples of input data for every output that you want to define. So for example, on this thermal image sensor that I've been having a play with, I've collected hundreds of frames of me walking around as a human. So I've labeled that as a human. I've also chased the dog around with a camera to get lots of frames of an animal. So these, once you have them, are called data sets. And these labeled data sets are then what are used during the training process to create an algorithm called the model, which maps its inputs to desired labeled outputs. This model generation is where, well, as I call it, the magic happens. It's the complex area. Generating these models accurately and efficiently is the subject of many university studies, and it's very complex. And this is where we need suppliers like Edge Impulse, because they have that expertise and they've managed to take the technology and make it more accessible to the general engineering community through the development of their online platform. So that's why Mihailo and Jenny will now take you through a bit more in-depth and a detailed explanation of how TinyML works underneath, and then show you the tool and how you can then implement that. So before I hand it over to Mihailo, I just wanted to mention the housekeeping rules that we've got down there. As you've seen, we are now recording this event, so everybody seems to be happy with this. Also, please make sure your mics are muted during the presentation. What we'll ask is that if you do have any questions, please save them for a question and answer statement when we have a gap, or you can type them in the chat box there and we will review them when we get to a natural break. So please use the comment box for that. Also, in the final Q&A session, I'd like to discuss more about applications. So if you're thinking about using a TinyML solution, then it's a good chance for you today to say, I'm thinking about doing this, do you think this is a good idea? And the experts here today will be able to tell you how suitable they think TinyML is, and maybe how the development flow will differ from what we'll show you in the demonstration.
So, what is AI and how does it link to machine learning? Now, when I speak to people about AI, a lot of people are, sometimes if they're not from the technical sphere, a bit scared because they're thinking of AI being kind of the superhuman intelligence. And the good news is that we at GigaDevice are essentially focusing on the section which is here called the narrow AI. That is essentially focusing on a subset of tasks which are very narrow in terms of what we are doing, and is fundamentally different from general AI or well, it's general AI as such called. General AI is more a complete system of artificial intelligence, which is much more close to human intelligence, and is definitely not part of embedded systems as such, because it's way too complex, and is essentially something we are not looking into as such at all. In that little kind of blue box on the left side is where embedded ML is sitting. and where we are using all sorts of mainly mathematical techniques to clean up signals, to provide those signals to machine learning algorithms, and then to implement them in a useful way on microcontrollers, microprocessors, but also on higher end hardware. So here is a bit kind of the historical context of what came when about, literally. We have this big term, artificial intelligence, and as I said, we have narrow and kind of the broad AI world. But within artificial intelligence, machine learning is, since the mid-2010s, something around about that, evolving significantly. And within a machine learning, you've got deep learning. Now, the interesting part about this is that I would say the last 5 to 6 years, a lot has happened to make machine learning possible outside the cloud on microcontrollers. And that is due to the TinyML work based off Google. Google has initiated this as a kind of an open source project. And one of our core ML heads is Daniel Sityuniake, who is also a founding member of the TinyML Foundation. And he was one of the pioneers in that context and is now with us, helping us to advance machine learning with his team into new fields where microcontrollers were never before. And we are quite glad and proud to have such a strong ML team on board here. I'm not reading out these texts because you'll have these slides after the call as well, so you can go through that as well. Let me just go to the next one. So how does machine learning work, and why is it good for? So when you look at normal programming, then you have to have a certain approach, which is you have inputs, and then you have your rules, which you code hard, and then you say if, then else, and so on. And then you have a certain outcome. Now, the cool thing about machine learning is that you kind of switch or swap things around by what Derek described, or collecting as much as possible data, which is kind of the red box here, which is the outcome, and telling what is kind of the, sorry, it's the input, not the outcome, it's the input. So the images which Derek has described as the input is what you kind of see, and the outcome is the label to the image, where you know, okay, this is a human being, this is a dog, and this is a fire. And the interesting part is that based off that, in machine learning, you get the rules. So you don't need to think beforehand a lot about the rules behind that, but the system finds out the rules for you. And that is very powerful, because you all of a sudden can do things with far less technical skills in terms of programming. And that makes it very accessible. Now, why is that kind of so cool to have machine learning working, especially on the edge? Well, you need less energy, you need less bandwidth, and you have far less costs in terms of transmitting the information, because you're doing all the smart and analytical work on the edge. By that, you're also increasing privacy, you're increasing the accuracy, because you're taking all the data in, which are coming straight from the sensor ideally, and therefore you're speeding up things as well. So in machine learning as such, you have different kind of approaches how to go about that, and just take my little pointer here. You've got two main fields, which is supervised and unsupervised learning. And I'm telling this mainly just to give you a little bit of context. You don't need to remember pretty much any of that, because our tool guides you very simply and easily through that, and it does it all in the background. However, I think it's good for you to understand, what is the theoretical concepts behind that and how does it work. And out of this approaches in supervised and unsupervised learning, there are several kind of mathematical and statistical techniques behind that. Now, what we see is that when we do these things, we do essentially a combination of two main things, which is digital signal processing, which is helping to take your data and clean it up for features, because we need the features which are specific to your problem. And these features are then passed on to the machine learning algorithms to be trained upon. And with that combination, we see quite some amazing results in the MCU world. And that is kind of the eureka moment for MCUs in a certain way, because MCUs aren't really expensive, but with the software, they can do a lot of smart things. And that is, literally speaking, quite game-changing. I addressed this topic of why does embedded machine learning work, and why is it important for microcontrollers? And I've mentioned that earlier before a little bit, but this is again kind of reiterating the fact, a little bit, when is ML in the cloud relevant and when is it on the edge relevant? And on the edge, it's always relevant when you have this blurb, which is bandwidth issues, which means if you don't have the bandwidth, then you better do the analytics on the edge. The second aspect is if you can't afford latency, because it takes time to send things to the cloud, process, and send back, obviously, then economics, which means if your processing on device is possible and you can afford that in terms of computational power, then it's usually cheaper than doing it in the cloud. Finally, the last two ones are reliability and privacy. On-device models are, in a way, more reliable because they just stay on the device and they are super narrow in their scope. And they don't depend on any connection to the cloud. And obviously, the last point, which is privacy, and that is all centered around, being able to do things without the cloud. And when you talk of Alexa, like Derek mentioned it before, you may not want to be recorded in certain situations or all the time, and you want to have certain things just processed on the edge. Well, guess what? This is where microcontrollers and TinyML and embedded machine learning come into play. So usually when we speak about machine learning, and this is true for the artificial general intelligence, especially for semantics understandings, you see kind of these images, and that's a Google image for a data center, but that's pretty much how their hardware with TPUs looks like for their semantics analytics. Now, as mentioned before, the reality of today looks already like this, which is on a microcontroller like this, we can process sensor data, audio data, and vision data. And the important aspect here, especially when you look at the market, which is currently out there, we are the only platform who can do all three of them at the same time, and everything is essentially developed in a way so it's integrated. So you can have either sensor and or audio and or vision. So there are use cases on which we are working at the moment, and one of them is the welding quality analysis, where we have some sensor data which is measuring the current during the weld process and the sound, how it sounds when you do the weld, and the thermal image, in order to tell if a welding process run by a robot is a good one or bad one. And even if it's after you've done that, you can say what was bad with it. So that is really powerful, and you can do all of that in a microcontroller, which makes it very, very appealing to industry. And we're talking to several large industrial conglomerates who are like really keen to see that working, because the device which does that in the end, from a hardware standpoint, is maybe a couple of $100, and that's it. The smartening comes from the data, obviously, but that's stuff which the companies generate themselves. Now, with that in mind, I think it's also interesting for you to see who are our current partners. And as Derek has mentioned, here's a selected list of partners we're working with. And I'm showing that at this point to illustrate essentially two things. One is, if this wouldn't be a relevant topic, all these big guys wouldn't jump on it. That's one thing. The other thing is, Despite the fact that we have these partners here on board, what we do is we provide you all the results as an open source C++ library. So even if you use an ESP32 or an Espressif board or something like that, you can implement things from the platform. Now, if you use one of these partners, it simply goes faster and easier. That's the main point. So, getting a little bit into the details, what is technically possible and what is required for, in terms of what kind of hardware you need for. On the bottom, you see an ascending character. On the left 3 sides, you see microcontrollers, and here you see microprocessors more mainly. Here is the kind of the low-tech end, and here's the high-tech end. Yeah. For an anomaly detection and a sensor classification, you can do that already in ARM Cortex M0+. If you want to do some voice and keyboard detection, you probably need a little more power, which is the M4, and so on. Now, in our ML work, we are with customers working on improving certain things and get possibly image classification going on an M4, so going down the technical complexity ladder, which is increasing the complexity for the software. But it's really interesting because for our customers, we see that they are appreciating that a lot because we help them drive down their hardware costs. And the same applies even for voice and keyword detection. We have one specific customer for which we have managed to get 3 or 4 words going on an M0 even, not as M0+, but an M0. And if you go a bit more upstream in terms of the complexity of the hardware, you can do more, obviously. You can do object detection on a Raspberry Pi and complex voice processing. So that's pretty much the upper end. The final end is obviously at the moment Jetson Nano, but we can run on any industry PC as well. That is not limiting us. The sizes you see here are the approximate sizes of the memory needed on the hardware for the respective task. So how does that work essentially, and what are the key metrics when you work with our platform you get from us? So we take, for example, sensor data off an accelerometer, and we pre-treat them in a certain way, which Jenny will elaborate a little bit in a second. And we then generate an ML model. And once we've done that, you get essentially 3 key figures. One is, how fast is that? 2 is, how much memory do we need on your RAM to execute the machine learning model? And 3 is, how much flash do we need to store local knowledge, which you may need in a case of classifying data and being able to say, that's the error A, or the error B, or the error C, for example, or object A, object B, object C. And you get that literally for every of the projects that you start with, because the first question is, what is the target and what is the hardware you want to work on? And based off that, all our calculations in the background are considering the performance metrics of the hardware against the use case you have. So where are we as a company? Well, we have more than 20,000 developers all over the world working with our tool, and they love us because we have a free tier. And in that free tier, you can essentially commercialize projects if they fit within our constraints. And the interesting part here is these guys are loving us because they can commercialize for free. So if you have a problem which is purely sensor data driven, and you've got an engineer who is happy to work with the forum as a source of question and answers, you can do that. The moment you start to have more complex models and you need our support, well, then you go into enterprise. But we'll discuss that in a minute. With regards to the projects, we have approximately about 28,000 on the platform where people have all sorts of topics. And especially if you go to Hackster.io and plug in Edge Impulse, I think there are more than 120 projects where people, without our knowledge, have done all sorts of things we never thought of ourselves. be it from medical applications where they attach a microphone to a stethoscope to listen to the breathing of people in order to estimate if someone has COVID or not, like a doctor, to robotics tasks. Pretty much anything you can imagine is up there. And that is really the secret sauce here, is that we are very open and transparent, and we have that free tier, and that's why we have this kind of very big success in this context. Now, where are we active and what are the business areas? Well, we have three main fields, right? So the first one is predictive maintenance. That is more than obvious. That's a typical use case where you can go into industrial applications. You look at current pattern analysis. Yeah, one of the topics we are working on heavily at the moment is motor current signature analysis for electrical motors, by which you can classify very easily and fast certain imbalances, bearing faults, misalignment, and things like that. That's one field, but then you can combine sensors and say, okay, I'm going to look at state of health and state of charge of a battery. Then you need current, charge, and discharge, heat in terms of temperature, and maybe information from a gyroscope. If it's in a car, is it uphill or downhill going? And all these things are typical predictive maintenance applications. The second area where we are active is asset tracking and asset monitoring. That is typical for logistics aspects, where you have goods at certain temperatures, and you know, the typical threshold approach doesn't really work that well, but the ML approach helps better. That's absolutely one application where we are active. But also in agriculture, we have a lot of use cases where people are using our image recognition to see if there are certain insects or pests around, or if some fungi are around in the process of growing vegetables, for example. You can do all of that with a microcontroller and a small cam and some training in order to, you know, be more targeted, for example, in your fungicide application. And lastly, one of our data side-wise biggest customers is a wearable company, a company called Aura. They produce a ring which you put on your finger, and it gives you a highly individualized recommendation in order to improve your sleeping pattern. And that's like one of the applications, but there are a lot of other interfaces where machine learning may make sense. And one of the key things for me in all of that, what we are discussing so far, you know, machine learning isn't always the best candidate. So it is in many cases, but I think it's more honest and more prudent to say, look, let's understand your use case first and put machine learning aside. And then once we've understood that, then we can revisit and see if machine learning makes sense or not. Having said that, I would like to hand over to Jenny, who will guide you through the kind of 4 core steps of the platform as such, and you see them here, and that's kind of the layout of the platform.
Yeah, so Mihailo gave a good overview of the motivations of embedded machine learning, but now I'm going to go into a little bit of like what actually happens and what the Edge Impulse Studio is actually accomplishing when we talk about embedded machine learning. So Edge Impulse is the complete machine learning platform. We do the entire life cycle from end to end, from collecting and labeling your data set, designing and training your impulse, building that and deploying it onto your device, and also testing it. All of it can be completed within the Edge Impulse Studio. So first, we want to make sure that we're collecting really robust, high-quality data sets with our sensor data on our microcontrollers or on our Linux devices, for example. We have almost countless ways of different options of how you can upload your data. Most common are people uploading from a CSV file or directly from their computer of files that they've already sampled from their device. It could be WAV files for audio, for example, or CSV files with accelerometer data, or even images that were taken from your phone or directly from the camera on your microcontroller. You can also directly integrate your cloud platform. If you use AWS, for example, you can pull data directly from your cloud platform into the Edge Impulse Studio and start building out your embedded machine learning models. And we take security super seriously here at Edge Impulse. Everything from end to end is your data. Edge Impulse does not touch any of it, even especially when you're connecting your own cloud. So this is the Edge Impulse design page. In this case, we're looking at the GUI interface of a accelerometer application. So we're looking at time series data from an accelerometer sensor, analyzing that time series data, extracting those features. Looks like my camera turned off, so let me switch my source. Sorry, 1 second.
You were fine. Oh, that's a different angle.
Yeah, yeah, the camera that I'm using overheats, so it shuts itself off. So I'm just going to do my MacBook camera, which is the same thing. Anyways, so this is the complete GUI version of what it looks like to completely design an end-to-end machine learning application for a microcontroller using the accelerometer data. In this case, we're looking at gestures for when you're taking the microcontroller in your hand, when you move it up and down. Is that an up-down motion? Is it a wave motion? Is it snake? Or is it idle, sitting still? So we can take the sensor data from the accelerometer on your device and analyze exactly what motion it is on machine learning on the edge on your embedded device. So this is the GUI version. On the left, we have normalizing our data, collecting our raw data, windowing over it and extracting those features. So we're slicing our data into windows, and for each window, we're going to say, hey, this is the features that I want for this type of motion, up, down, for example. We're also going to resize it if we're looking at images, for example. We also have a new feature that's not shown here for downsampling. So you can also upload data at any frequency and downsample it all to be the same frequency. So it makes collecting data from multiple types of sensors really easy. The white column here is our data pre-processing. So this is the block where we're going to take our raw data using signal processing techniques, extract our features using a pre-written Python code, and pass those into our neural network algorithm. So in this case, we're going to do the spectral analysis because we're looking at motion data. But we also have pre-written blocks available for you to do image processing, audio processing for keyword spotting, for example. And you can also use your data raw as is. So the purple block is learning from your data. The machine learning code is pre-written here, available for you to use to extract from the extracted features of your digital signal processing block, train on those features and analyze different patterns in your data to do classification. So what type of motion is it? You could also do other types of neural network blocks here for images such as transfer learning or even anomaly detection. Analyzing a gesture that wasn't necessarily trained by the model, anomaly detection will show a score showing that that gesture wasn't what the model was trained on, but it looks different from the rest of the model. Now we're going to save our impulse and get our conclusions. And this includes an array of different probabilities of all the prediction score outputs of our gestures that this model was trained on. So data-driven engineering is really important here because Edge Impulse makes the machine learning training really easy. So we want to make sure that the data that we collected is super high quality and robust. You can also deploy anywhere using our different deployment options that we have in Edge Impulse. We can deploy via C++ library that includes no third-party tools or other third-party libraries. So it's completely open source and there's no black box in Edge Impulse. You can directly flash that onto your microcontroller as long as your microcontroller can build a C++ library into your application. You can also deploy onto a Linux device, or you can also deploy into mobile and WebAssembly applications where you can directly deploy your model in your web browser and start classifying new data directly on a mobile phone, for example. So Edge Impulse contains an entire MLOps ecosystem available for you to use. Almost everything you see here is available for you to use today if you create an account on edgeimpulse.com. There's a little complicated this picture, but it'll make more sense when I go through the demo. But essentially, in the middle, you have your complete machine learning lifecycle from collecting and labeling your data set, building and training your algorithm or your impulse, testing your impulse, and then deploying it. We also have a couple features available directly in the Edge Impulse Studio called the Eon Tuner and the Eon Compiler. The Eon Tuner is a relatively new feature that we've added into Edge Impulse, where essentially we can take sensor data that you have uploaded into your project, and based on that sensor data that you have uploaded, directly find a model and DSP parameters that fit that data instead of trying to fit your data to the algorithm. We do it the other way around. So it's essentially called AutoML, and it's a really valuable tool in order to further increase the accuracy and decrease the size of your model, which is size is super important for microcontroller applications, especially. And the Eon compiler, again, we're focusing on size here. The Eon compiler completely reduces the size of your model from about 25 to 55% compared to models that were compiled with the TensorFlow compiler. So this is our own custom compiler. We've identified pieces of code and certain memory optimizations that were not needed from the TensorFlow compiler and have removed those redundancies to completely reduce most models by 25, 50, 55%, and without affecting the model's accuracy at all or performance at all. And then you can also integrate any of your other deployment tools like CI and test optimization. You can also deploy with your own custom blocks, which I can show you in a second. And you can also integrate your own custom DSP blocks as well, and your own custom machine learning code. So nothing in Edge Impulse is a black box. Almost everything is configurable. And if it's not configurable, we could probably make it configurable for you. So what I was mentioning, this is the Eon Tuner. A lot of the embedded ML tools on the market today just focus on machine learning, but in the case that we're looking at here, our AutoML tool is not just machine learning. It's focusing on both the DSP aspect and the machine learning aspect. DSP is super, super important for MCU-based embedded ML because we will need to optimize the amount of sensor data that we need to process because it's all happening directly on the device rather than in the cloud. So our AutoML tool goes through and generates hundreds of possibilities of different combinations of DSP parameters and neural network layers in order to find the best type and best combination for your specific data set. So it's a really, really valuable tool, and it's available for you to use free today. So this slide is basically just saying, hey, in today's current times, if you're just going to use a TensorFlow on its own without using Edge Impulse, it's going to take you about 3 man years to complete this entire life cycle in this process. Using Edge Impulse, you can take it down to a month. So it's super, super easy. And I even do it in just a few minutes for most projects. So I'll show you that in a second. We also have tons of different deployment options, which I'll show you in the demo, but we have a bunch of officially supported boards for Edge Impulse deployment. These officially supported boards include things for if you're using one of our 3 types of officially supported sensor data, you can directly deploy a proof of concept binary onto one of these boards that does inferencing on the edge on your device without having to write any code at all. So it makes a pre-built binary for you that you can directly drag and drop onto your device and start inferencing based on your sensor data that you've uploaded into the Edge Impulse Studio. If you're not using an officially supported board, we have a bunch of different options for you to deploy your model. We have the C++ library that is completely open source, no black box. All of that code is available for you to use. It comes with all your DSP and all of your neural network code. Same for the Arduino library, WebAssembly for your mobile phone or for your browser. We also have OpenMV for image applications and STM32Cube synthesis packs for ST boards. So those can all be directly integrated into whatever application that you're developing, either for embedded or mobile or for images, for example. In case this seems all really overwhelming, we also have a Coursera course where you can become an embedded ML expert today without much experience at all. As long as you know how to compile for a C++ application, you should be able to follow along with this course. So I recommend checking those 2 courses out, and then I'll hand it back over to Mihailo, where he's going to talk about our business model.
Perfect, thank you. Since Derek has brought up the use case topic, I've just inserted 3 slides on the use cases just to kind of open up kind of the view. Let me just share that with you now. Just to show you, and then we can jump into the kind of commercial side of things. Come on. Okay. So as I mentioned earlier, just get my laser pointer. As I mentioned earlier, you know, sometimes it's difficult for people to imagine where these things are happening. And what we've done is we've looked at various applications. You know, this is not an exhaustive list, but it's an interesting list in my opinion, where we're looking essentially at the application, then we're giving a bit of context, then what kind of sensors are involved in that. And we're giving you a little bit our point of view, is machine learning here relevant or not? And that comes back to the initial discussion where we said, look, it's not always necessary to have machine learning. So I'd say the first 3 cases, we actually have projects going on where we, for this first one and for the third one, we have even so-called public projects, which means you can go to the platform, sign up, and use the data which we have there and play around and see how we did that in order to get to certain results. And that's one of the nice features here, is that you can clone projects which are public into your own account, and you can straight away work with that. So as I said, these slides will be shared with you. We have 3 slides of those. So this is the industrial area where we see things: motor current signature analysis, MCSA is one field. Battery and battery health is something which we see definitely happening in the market. Welding quality analysis I've addressed. Now, indoor quality is something which is often asked. Our assessment was, well, not really needed, because we think mostly here threshold values are enough. But again, you know, there are certain use cases where it may be relevant, but I haven't seen them so far. That's where we came to that conclusion. Indoor and location, you can do things here again without ML in our opinion, and so on. So this is one slide. Here's the second slide. That's the section of environment and logistics. So I won't go through all of those, as I'll just share that with you as food for thought. And I think once you've gone through those and you've identified potential use cases, just feel free to come back to Derek and us, and we'll arrange an individual call. And here's another section, which is essentially security and emergency, wearables, animal well-being, and smart home, and you know where we see these applications. So that was kind of the quick use case collection. Now I'm jumping to how does that commercially work. So we've got essentially 2 tiers. One is developer and 2 is enterprise. The developer has these red marked limitations. So as a developer, and everyone can sign up and use the developer account. It's for free, as I mentioned earlier. You have the limitation that you can only do 20 minutes of a compute time, which you can use to solve your problem. What does that mean? That doesn't mean the time you are on the platform. It simply means the moment you upload data and you want to filter the data, we need to rev up machines for you, and that's our Kubernetes based infrastructure for the ML pipeline here, which costs us time and money in an Amazon cloud. And that's where the compute limitation comes from. So these 20 minutes per job per month are the limitation for the first limitation. The second limitation is the data size. So usually for vibration and even some sound data, 4 GB is enough. But if you go into more complex video-based or image-based classifications, for example, the data size of 4 GB may be quite limiting, and you need to go enterprise. And the third important aspect is that you have here the community-based forum. Now, the forum as such is quite active and is very good, and we've got people like Jenny and others from the user success team who are also working in the forum to answer certain questions. But the moment people want to go really dedicated, they need the enterprise-grade support, and that's where you enter Enterprise. And Enterprise has 3 tiers: hybrid cloud, private cloud, on-premise. So what's the difference? Hybrid cloud is the standard which I'd say 90% of the people go for. And that is essentially an Amazon S3 bucket from us assigned to your organization, where you can upload your data and do all the data management, because that's the really important part in machine learning, to understand that data is your lifeblood. And you need to know what has been used where and for what, with which result. And that's why we are giving you here an account, and you store your data and you work off that basis. Once you've done all the training, you can download it into a C++ library onto your laptop and then deploy it anywhere, as Jenny has described it. Here we ask for a minimum of 3 projects, and we charge per project. So a project is $3,000 per month for a minimum of 12 months. Then there we are limiting the compute time to 10,000 minutes. The background of that is that we want to avoid being in a problem that after 10,000 minutes, we are just, getting random calls of certain functions. And by that, we simply pass on the cost which we have from Amazon at the same rate to the customer. But that's usually for pretty much, I think none of our customers ever have reached that limit. So that's way plenty. Data set size is unlimited for all of those. And the real important part here is you've got enterprise grade support. And that's, again, an important aspect in this discussion is we are not a design house. So it's not our task that you unload your data onto us and we do the solution for you. We are a software as a service company, which means we will help you along the way with one of your engineers to work on your use case to solve the problem. And that serves many really valuable kind of goals. And one of the most important one is creating in-house knowledge of the product, which stays within the company, right? Because we are not in your industry, in your business, so we don't have all the ins and outs, but we have the ins and outs, how to get it working on the platform and then on the hardware target you're looking into. The private cloud is something where people are working on very data sensitive projects, where they say, you know what, we don't want you to host that Amazon cloud, we've got our own system. Now, the interesting part about this is that we are essentially replicating all the infrastructure we've done here for many users, and you've seen that we have more than 20,000. And that's why this is quite expensive, and that's $20,000 per month on top to the minimum of projects, and these are like 10 minimum projects. So that's around about $50,000 US a month with quite a long commitment. The last one is a very rarely used one, but we do have some of those, and these are mainly government projects where we do on-premise. Now, if you have ever been in the software as a service business, then you will know that on-premise is the most painstaking and resource-absorbing one. So this is why it's really based on availability only. And this one starts right away with $50,000 a month plus 20 projects, 3,000 each. So that's another 60,000. So that's 110,000 a month. And you can guess that this is not a ticket a lot of people are signing. But there are governments out there who are working with different agencies and saying, look, that makes a lot of sense for us. I think it's important to mention this last or pre-last aspect here, which is the API access. All what we do is essentially available through an API. So you can do, if you know how to do that, really cool by calling up API functions and be very fast in the development process. So I think that's all what we do in terms of the typical engagement between developer and enterprise. There's one feature which is relevant to people who want to offer that to their customers, and that's called white label. Now, what is white label service? So your logo could be here, and you could have your own hardware for which we have developed tutorials and integrations and so on. I'm not sure if this is relevant, but that's another service which we offer where the front end can be yours, but the back end is Edge Impulse. I think with having said that, I should park here, and I've seen maybe a question being asked. I'm not sure. Okay, Jenny, you've dealt with that already. Thank you for that. I would suggest that you take over now to do the presentation of the accelerometer and fan. Yes, and how you do that. Perfect. Thank you.
Sweet. So before we get started into the live demo, I wanted to point out a couple of things. This is our homepage of the Edge Impulse website. You can get started building out your data set and deploying to your own microcontroller today for free if you sign up on this website right here. You can also scan this QR code on your phone and get started building a model without even signing up and build it within 5 minutes. So I recommend giving that a try. But this is the main homepage. All the information about all of our use cases and everything are available here. But if we move on to the documentation, you can see exactly every single one of our boards that we quote unquote officially support on our documentation. Of course, like I said, you don't need an officially supported board in order to get started with Edge Impulse. You can get started with any board as long as it has enough flash and memory allocations for it, and that you can compile a C++ library into its application. So this is the documentation. I recommend checking it out. And today we're going to be specifically looking at a Silicon Labs Thunderboard. So we also have a bunch of documentation for this, how to get started, how you flash the latest Edge Impulse firmware in order to start collecting data directly over serial connection to the Silicon Labs Thunderboard and uploading it into your Edge Impulse project. So I recommend checking that out. And also, like I said, all of our firmware and our code is available for you open source to use. Nothing is private in Edge Impulse. So as you can see here, this is the firmware that we can build from the studio that integrates your machine learning model for the Silicon Labs Thunderboard. And all of that is available for you to use at your disposal on our Edge Impulse GitHub. And we have similar repositories available for you to use here for all of our other officially supported boards and some boards that we don't even officially support. So check out our GitHub for that as well. And let's see, moving into the Edge Impulse Studio now. So this is the Edge Impulse Studio dashboard. For every project in Edge Impulse, one project is equivalent to one machine learning use case. So like I showed in the slides, that was a use case for gesture recognition using motion from an accelerometer. Today, I'm going to be looking at vibration monitoring for a fan using the Silicon Labs Thunderboard from the accelerometer. So it's very similar to the one that I went over in the slides, but it's just looking at vibration of a fan rather than gesture detection. So this is the dashboard. You can see here that we have explicitly written out details of how you can acquire your data, design and train your model, and finally deploy. This option right here this section will change depending on how close you are to finishing. It'll show a little percentage. You could also add your own collaborators of your team members. If you're in an enterprise organization, for example, I can add my other team members available here. And you can also transfer it into an organization. This is just on my own account though, so I'm just the only collaborator. But collaborators allow you to share your project with all of its data at this point in time to your other team members and share all the exact same results of your neural network training and your model testing, for example. And again, nothing in Edge Impulse is a black box. If you know anything about machine learning, you can download these intermediate files here for use in a Python script or in TensorFlow. So moving on to the Devices tab, there's a bunch of different ways you can upload your data, like we mentioned. For this project, I directly uploaded my sensor data over serial connection using the Edge Impulse CLI with the Silicon Labs Thunderboard directly into my project. I'll show you that in a moment. But basically, I went into my terminal, I typed in Edge Impulse daemon, and I did some configuration steps to connect it into my project. And now, simple as that, my Silicon Labs Thunderboard is connected to my project with the green light here, and I can start acquiring new data. So this directly pulls from the sensors available on my Silicon Labs Thunderboard, uploads them into my project over serial connection using our Edge Impulse APIs. We can also upload things like CSV files or images or WAV files for audio, for example, directly from your computer. You can also connect directly to the bucket of your Amazon Web Services, cloud platform, basically anything. The options are endless here. So for this use case, I have collected 4 different types of data or 4 different classes for our machine learning model. I have collected off data for when the fan is off. I have shaking motion for when I'm shaking the fan. And here's, if you can see my video, this is sort of what the fan looks like here. I have a Silicon Labs board taped onto the top of a USB powered fan. Pretty simple. So that's shaking. Nominal is when the fan is just behaving normally. There's nothing wrong with it. It's just moving back and forth and spinning at a low or high speed. And then obstruction is when I'm putting a pen or pencil into the fan's blades and determining what that motion looks like or that vibration looks like from the Silicon Labs Thunderboard and uploading that into my data set. So this is all my training data set for my machine learning algorithm. I also do that same thing for my test data. And I can show you how easy it is to upload new data simply by starting to sample. So I've already connected my Silicon Labs Thunderboard over the Edge Impulse CLI. It was super, super simple, by the way. All I had to do was flash a firmware that was made to do the ingestion of my data into the Edge Impulse project. Did some configuration of logging into my account and setting my device name and selecting my project that I want to upload to. And now I've gotten to this point. We have instructions for all of that available on our website as well. So I'm going to turn on the fan here and we're going to record a new sample for nominal operation. It's as simple as clicking start sample. You can see here that a request was sent to my device. It uploads the data and you can see exactly what that sample looks like directly in real time. I just took it from my device. So it's super, super easy to collect a really high quality and robust labeled data set of assorted different samples for your use case. So I've already done that for all of my classes here. I've done it for shaking, nominal, obstruction, and off for both my training data set and my test data set. You want to have about an 80-20 split between the size of your data set over training and test data to make sure that you get a really accurate image or accurate deployment of what it would look like in real life or what the vibration would actually be when you're deploying it into the field. So moving on to the impulse design, this is where we, like I showed you in the slides, do the GUI graphical interface option for the life cycle of our machine learning project. So over here on the left, we have our time series XYZ accelerometer data. I've set my window size and window increase, and I'm not doing any downsampling because all of my data has been recorded at 100 Hertz. And then on the right, but you can downsample to any size, any Hertz value that you want, 62.5. All of that is available within the Edge Impulse Studio. So if you want to upload data from multiple different frequencies, you can have them all balanced at the same frequency directly in this tool right here. So spectral analysis is where we're going to do our pre-processing. These are just GUI blocks that are wrapping around Python code that we've already pre-written available for you to use for free. So we have a bunch of different types of blocks here. I'm using the spectral analysis one for accelerometer data, but we also have other types of processing blocks for audio data, for example, for keyword spotting, or spectrogram for other types of continuous frequencies that are not necessarily accelerometer data. You can also do raw data, which is not doing any pre-processing at all and just using your data as is and extracting those features. And then we also have the ability to add your own custom block. Say you know how to write Python code and you want to do your own special pre-processing. That's available for you to add into Edge Impulse as well by following our instructions on our documentation. So what we're doing here is we're just taking the signal, taking the raw signal and smoothing it out so the signal is not as messy and there's less for our machine learning network to train on. So our purple block is now our neural network block or our machine learning algorithm. We're taking the neural network classifier, taking the extracted features from our spectral analysis block and outputting, mapping these features onto 4 different classes: nominal motion, obstruction, vibration, off, or shaking. So we're mapping these extracted features from our DSP block onto our 4 different types of vibration classes. We could also add other types of blocks here, and this section will change depending on the type of sensor data that you have uploaded. But today I'm just going to do classification because I want to analyze different patterns in my accelerometer data. I could also add an anomaly detection block here. So say I trained my model on a type of vibration that wasn't say I trained my model and it's now detecting a type of vibration that I didn't train my model on, an anomaly detection score would pop up with that saying that, hey, this looks like it's an anomaly. It's something that you didn't train your model on. Maybe you should check that out. And there's also regression available for you to use and transloading for things like images. So I save my impulse and I'll move on to the DSP page. So like I said, this DSP page is just basically filtering your data and making it smoother so it doesn't have, so the machine learning network doesn't have to train on so many different points in your data. So it's taking this really messy, high frequency signal and smoothing it down to something that is more manageable for our neural network to train on. All of these parameters are just other separate parameters into a Python function that we have pre-written for you. So you can change these here, but I didn't change any of them. I just used the default options that we have in Edge Impulse when you click on the block. But these are our raw integer or float value features. And after we filter it, these are our process features. So it sort of normalizes our data for every single piece of every sample that I've uploaded into my project. I can also see how long this filtering will take directly on the device after I deploy with the signal processing code that is included in the Edge Impulse SDK. This processing time will only take about 17 milliseconds to get from this messy raw signal into the smoothed out signal. So 17 milliseconds of processing time and 5 kilobytes of RAM usage. So it's pretty efficient, especially for accelerometer types models. You'll see that the processing time increases depending on the type of sensor data that you have uploaded and how complex this data is. So I've clicked on the Generate Features tab, and I've already clicked Generate Features. And this basically extracts all of my features from my raw data based on the signal processing code that I've selected. And I can see that I get a Feature Explorer visualization on the right here that sort of helps me determine if my data is really high quality and robust and separates nicely even before I do machine learning on it. So just from signal processing, I can already see that my 4 separate classes are really clustered nicely. And so this is my obstruction, this is my shaking, this is my nominal motion vibration, and here is what it looks like when it is off. And I can click on each individual dot here, zoom in, manipulate the graph, and see exactly where each sample window is coming from in order to generate this Feature Explorer. So this is just a really valuable tool to make sure that all of my data is labeled correctly. Say I had an obstruction vibration that was mislabeled accidentally as shaking, it would pop up over here and it would look interesting. The graph would look wrong. So that would mean that my sample was actually mislabeled. So this is just a really valuable tool to ensure that your data set is really high quality, because like we said before, data-driven engineering is really important here because we've made the machine learning part so easy. Moving on to the neural network classifier. I've already trained my model, but this is essentially, again, a GUI that is wrapping over Python code. So I've typed in the number of training cycles that I want to train my model on, and its learning rate, how fast it learns, how fast the neural network learns. In this case, I'm just doing 2 dense layers. Don't want to get too technical here, but this is just the default of what happens when you select neural network classifier in Edge Impulse. The only thing I've trained here is the number of neurons, but you can add other types of layers, and these are just Python snippets that you can drag and drop without having to write any code. So all of these layers are available for you to use here. But say I know how to write Python code and I know how to use TensorFlow, I can also type code directly into my web browser in the studio by switching into expert mode. So I can type whatever Python code I want into this editor, and then all I have to do to see this similar output over here is click Start Training. But I don't want to write Python code today, so I'm going to switch back into visual mode. All I did was click Start Training, and now I get to see this lovely confusion matrix over here on the right that shows the percentage of my training data set and versus my validation set that were correctly labeled or correctly predicted. So 96%, 96%, 100%, 97% of my classes were correctly labeled by the trained model. You can see down here, most of these dots are green, meaning that they were labeled correctly. Down here, the red dots are ones that were mislabeled or labeled incorrectly, meaning the machine learning network sort of got confused on what this sample actually was. Was it obstruction or was it supposed to be nominal? So in this case, in order to make this model even more accurate and better at predictions, I would need to upload more data with more samples that look similar to this one, for example. Or I can move the sample into my test set and say, hey, I don't really ever see that type of motion often anyways. Let's just take it out of the model and we don't need to train on that. So the Feature Explorer makes iterating on your model and refining your data set super easy and quick, all in Edge Impulse. And on the bottom, we can see, similar to the DSP page, how this piece of code or this neural network will perform on the device that I've chosen on the dashboard. In this case, for the Silicon Labs Thunderboard, it's going to take about 1 millisecond of inferencing time to get from the extracted features into a predicted label. And it's going to take about 1.7K of RAM and 18.7K of flash. And this is basically just, depending on your sensor data, depending on your raw data that you have uploaded that you're taking from the board, how long does it take to get from raw data through the DSP block extracted features into your neural network output your predicted label. And the flash is just dependent on how many basically matrix multiplications it takes in the SDK in the Edge Impulse SDK using TensorFlow and Keras. So this is the neural network classifier. I can also directly classify data live within the studio without having to do any deployment to my microcontroller. So I can classify existing test samples that I've uploaded in the studio by selecting one of these from the dropdown, or I can classify brand new data directly from my Silicon Labs Thunderboard that I have connected over serial connection from its built-in accelerometer sensor, whatever sample length I want. The trained model, and the web browser don't know this new data at all. So I can start sampling brand new data and it's not labeled. So it has to do machine learning to figure out what type of motion it is. And I'm basically doing shaking right now. So let's see if it gets it right. I've uploaded brand new data and it's correctly identified it as shaking based on my trained model. And this is brand new data. The neural network has never seen this before, and it's not in my test set because it's called testing. So the expected outcome is testing because it doesn't know what the expected outcome actually should be. So this means our model is performing really well already before we even deploy into the field onto our device. We can also bulk test our model with all the test data that we have uploaded on our data acquisition tab. We can just click classify all, and this passes all of our test samples into the trained model and outputs the percentage accuracy, depending of all the windows of the data that I've uploaded and its predicted result. So in this case, we have about 94% accurate, which is really good compared to the expected accuracy that our neural network classifier page said, which is about 95, 97%. So this is actually looking really good. And now that I like the way this model is performing, I'm going to deploy it onto my device. But before I deploy, say I want to add more types of vibration to my model, but I already like the way it's performing right now, and I want to make sure I can go back to it in the future if I want to. We have this versioning tab that lets me bundle up all of my data, all of my labels, all my DSP parameters, all of my neural network layers, wrap them all up basically into a GitHub repo or a zip folder, for example, and wrap them up all into that zip file, for example, and you can restore your project to that exact point in time with all of that same data, all those labels, all those parameters at any point in time by clicking on restore here next to your version that you want. So I've already done 3 different versions here. This one from this morning had about 98.9% accuracy, but it wasn't super good once I've deployed. So then I sort of refined my model based on the results that I was getting from my deployed binary and changed up my training data set a little bit. So if I wanted to go back to version 1, for example, all I need to do is click on restore. And this is completely available for you to do in Edge Impulse. So it makes really iterating your model, refining your model, and going over the machine learning lifecycle and pipeline over and over again, really, really quick and safe because your data is secure and you can see the history of it at any point in time. So now that I've versioned my project, I want to be able to deploy onto my device. So today, since we're doing the Silicon Labs Thunderbird and we're doing accelerometer data, this combination of sensor and board is an officially supported option in Edge Impulse. So of the available options that I can do on the deployment tab, I can choose a pre-built proof of concept, ready to go binary that I can drag and drop onto my device and start doing inferencing of my accelerometer data on the edge without having to write any code. Let's say I'm using an MCU that is not officially supported, or a type of sensor data like a Doppler radar or a gas sensor, for example, that is not officially supported by Edge Impulse. I would choose one of these libraries here up at the top and do some embedded engineering and coding to integrate these libraries into my own application code and then flash them onto the device. But we have documentation for how do you integrate the Edge Impulse SDK, all available on our website. So the C++ library is a portable C++ library that contains no external dependencies and is completely open source, no black box. All the DSP code, all the neural network code is available for you to use and see and flash onto your board, integrating via how you would normally integrate a C++ library into your application code. For many boards, you can also integrate an Arduino library, which just makes it even easier. And then we have for ST boards, a Synthesis Pack, WebAssembly for doing inferencing of your model directly in your web browser, like on a phone, for example, or even on an iPad or a laptop. And then we also have an NVIDIA TensorRT library available for you to deploy your model onto a Jetson Nano, for example, for Linux operations. So today I've chosen the Scilab Thunderbird Sense 2 option. And if we scroll down, I can see all the optimizations that have been achieved with this model with the Eon compiler. So without the Eon compiler, and I'm just using the TensorFlow compiler, this model for accelerometer vibration detection is going to take around 32K of RAM, 32K of flash, and 2.7K of RAM. But using our custom Eon compiler that just determines and removes all the fluff, but maintains the same accuracy, it reduces it by about half to 18K of flash and 1.7K of RAM. And size is key for microcontroller applications, especially because you don't have much memory available for you to do machine learning. So decreasing the size while maintaining performance and accuracy is really important. So all I've had to do here to get this pre-built proof of concept binary flashed onto my board is click build, and I've already done that. So you can see here, all it did was download it. I get Scilab's fan monitoring Scilab's Thunderboard, P5, bin file. I open up Simplicity Studio 5, uploaded the application, and then again, from the command line, using the Edge Impulse CLI, I can directly start inferencing accelerometer data from my Silicon Labs Thunderboard by typing Edge Impulse run impulse. And then this is going to start the main application that takes new raw accelerometer data, passes it through my trained model, and spits out a prediction score for what the model thinks this type of motion or vibration is. So right now I have the fan running normally, and it's successfully predicting that the type of vibration is nominal. I can start to shake the device, and it's going to start to show that the correct vibration is shaking. And all of this is machine learning predictions that are done directly on the edge, directly on my Silicon Labs Thunderboard, all of it based off of what I was trained in the cloud, using those mathematical predictions on the device. So nothing's happening in the cloud. It's just taking what was trained in the cloud and passing it through and doing it directly on the device. And you can see here how long each portion of the process takes in milliseconds as well. And then I can also do obstruction by putting a pen into the blades. Sort of see the video. And it's correctly identifying what that type of obstruction anomaly is. Is it shaking, or is it obstruction, or is it nominal? I'm going to shake it again. And it's correctly identifying it. And that is Edge Impulse and embedded machine learning on the Silicon Labs Thunderboard for fan vibration.